In this video, we're going to be doing some extra Lagrange error-bound practice. So the first one is saying, suppose the Taylor series for f of x, which is centered at x equals 0, converges to x equals 1. It's known that the absolute value of the nth derivative is less than or equal to n over n plus 1 when x is between 1 and 4. Interesting. So, what about when x is near 0? I think I must have typed that in wrong, and I think I'm going to go with 0 to 4. Because I can see that that's my typing. I know this was an online quiz. Let me just. Yeah, I must have typed that in wrong. Maybe that was supposed to be. I don't know. Let's see. Yeah, it's supposed to be 0 and 1. I think I may have just typed something wrong. Maybe it was supposed to be 0 to 1 like that. That would make more sense. Okay, so error, which is exactly what this is. Error is less than or equal to. Well, what have I got? I've got used a third degree polynomial centered at x equals 0 to approximate f of 1. So it's something divided by the next factorial, absolute value of 1 minus 0 to the fourth power, and then that maximum value of the absolute value of the fourth derivative. So we're saying that f's fourth derivative is less than or equal to 4 over 5. So that's 4 fifths divided by 4 factorial times 1 to the 4. That's like 4 fifths multiplied by 1 over 4 factorial. We should be able to find that in our answer choices. There it is, answer choice B. Okay, the next one. This is the example I've got of one. Then originally I think this was a multiple choice question, but this one requires a calculator, obviously with the 3 decimals there. If we're using the fourth degree Taylor polynomial centered at x equals 0 to approximate f on the interval 0 to 1. Okay, so x0 is somewhere between 0 and 1. Okay, we wouldn't use 0, okay, but we could use 1. Okay, and the Lagrange error bound for the maximum error bound for the, and I typed this one wrong too, because that's not a valid English sentence. Basically, what's the largest error that we could get in approximating on that interval? Okay, and we know the next derivative, so it's going to be error less than or equal to something divided by 5 factorial times the absolute value of x0 minus 0 to the fifth power. Well, the biggest that the inside of that absolute value would be 1 minus 0 to the fifth power, right? Because if I took a fraction to the fifth power, it would be even smaller. And so I'm going to maximize that by plugging in x equals 1. Okay, the next derivative, I'm looking for the maximum absolute value of the next derivative, which would be f's fifth derivative. Maximum absolute value of f's fifth derivative of x when x is on the interval 0 to 1. Well, so that's really what we're trying to do, is find the maximum value of the absolute value of e to the sine x. Well, e to the sine x is always positive. You could use a calculator for this, but I don't think we need to. I mean, I guess if this was an online quiz and we were typing our answer into 3 decimals, we might as well, if we were going to do it to find the value eventually, might as well just graph the thing on the interval 0 to 1 and see what the absolute maximum is there and divide it by 5 factorial. But I know that sine of x is an increasing function on the interval 0 to 1 because 1 is less than pi over 2. E to the thing is also an increasing function. And so that would be e to the sine of 1. And so that's what I'm going to plug in here, e to the sine of 1. And then, if we needed to find the value of that, we would get 0.019. Okay, so 0.019 would be that Lagrange error bound. So it would be pretty accurate, is what we're saying. All right, here we've got one, it looks like another. Oh no, I think I just replaced a which of these with a what. P is the fifth degree Taylor polynomial, so we're using a fifth degree centered about x equals 0. We're going to approximate f at 1.2. Okay. So Lagrange error bound, error is less than or equal to, okay, the next factorial absolute value of 1.2 minus 0 to the next power, and then we want the maximum possible absolute value of the sixth derivative. Here it is, printed on the paper for us, 58.8. Okay, and then, I think that's just going to be good enough for us, right? I have a feeling this was originally a calculator question, and you could have typed that in and figured out which of the numbers was right. But for us, in an open response scenario, that will be plenty, so we're just going to stop there. Yeah, we did not need to show it was less than or anything. Yeah, we're all good. All right, suppose g is an antiderivative for f with g of 0 equals 5. Okay, use the fourth degree Maclaurin polynomial for g. Okay, so f would be, I'm going to write it kind of the other way, 9 minus 14x plus 12x squared minus 8x to the third plus 1x to the fourth. But we won't really be needing that. G is an antiderivative for f, so there will be a plus c. 9x minus 14 over 2 would be 7x squared, 12 over 3 is 4x cubed, 8 over 4 is 2x to the 4. I know I must be doing something right here. I'm going to mentally take the derivative because I went fast there. Yes, that looks all good to me. All right, and I'm going to say, all right, well, it told me g of 0 equals 5, so 5 equals c plus 0 minus 0 plus 0, and then I'm realizing, okay, all the rest of these are going to be a bunch of zeros, so c equals 5. Okay. Or you could say that the first term of the Taylor series for g around x equals 0 is going to be g of 0, which equals 5. Either way, that's why I've got a 5 there. And now I've got that. G of negative 0.5 would be 5 plus 9 times negative 0.5 minus 7 times negative 0.5 squared plus 4 times negative 0.5 to the third minus 2 times negative 0.5 to the 4. And there we've got ourselves a fourth degree polynomial for g approximating g of negative 0.5. Okay, if the fourth derivative of f, okay, I've been waiting to see one of these because I know I had one similar to that and I have not seen it come up this year. Okay, so f's fourth derivative is less than or equal to 1 for you. Like, why? I just used a fourth degree polynomial. This is off. Okay, the Lagrange error bound for my approximation, let's just go in here and think about my approximation. I used a fourth degree polynomial for g. I was centered at x equals 0, and my approximation point was x0 equals negative a half. Okay, what I need to get my error bound, I'm going to just set up for everything I need. Divide by the next factorial, absolute value of 0.5 minus 0 to the fifth. Here's one where we needed those absolute values. And then there's going to be some m in the numerator. And I'm going to have to figure out what that is. Now, m is going to be the maximum absolute value of g's fifth derivative. And you're like, okay, well, they gave me f's fourth, maybe I can figure out if f's fourth is equal to g's fifth. All right, so if I know that g is an antiderivative for f, yeah, then I know that if I take the derivative of g, I'll get f the first time. G double prime is going to equal f prime. G triple prime will equal f double prime. Okay, there we go. That's why g's fifth derivative equals f's fourth derivative. Okay, so this is going to equal the maximum absolute value of f's fourth derivative, which is going to be 140. And then we can just go ahead and put that there. This was kind of just what we were thinking through, and there we go. And now we've got ourselves, that's the Lagrange error bound. If this was an online quiz, we would type it in and get ourselves a 3-decimal number, or maybe not. 32 times 5, no, that's definitely going to be a decimal. And I'm glad we're not finding it, we're just finding the value. All right, this one's very similar to one that's on the homework, but I don't think it's exactly the same, so I'm gonna still do it. Use the line tangent to the graph of f at x equals 3 to approximate f of 2.5. Well, the line tangent is the first degree Taylor polynomial, so I'm gonna say, f of x is gonna be approximately equal to, and I'm just gonna start with the tangent line as the first degree Taylor polynomial, f of 3 plus f prime of 3 times x minus 3 to the first, whoops, something minus 3, plus f double prime and stuff like that. But for now, we're going to use the line tangent to the graph of f to approximate f of 2.5. Okay, so 6 minus 10 multiplied by negative half, that would be 6 plus 5, which would equal 11. Okay. And then we're going to use a third degree Taylor polynomial for f centered at x equals 3 to approximate f of 2.5. So we need to go up to second derivative, second factorial, second power of something minus 3, plus third derivative, third factorial, something minus 3 to the third power. And that thing that we're plugging in, that was 2.5. Okay, now I'm going to say, man, I think I'm just going to 6, that was a plus 5. 16 over 2 factorial is 8. Divided by 4 is 2. 24 over 3 factorial is 4. Times negative 1, so I guess it would be positive 1/8. I think that's plus a half. Okay, I may have made an arithmetic error in there trying to fit it into the line, but you know, that expression right there that's my true answer. In case I made an error. Whoops. Oh, I don't know what's going on here. Okay, I just want to erase. All right, so is there enough information to determine whether f has a critical point at x equals 2.5? No. Okay, I only have derivative information about f at x equals 3, and there could be, there could be some weird behavior happening, okay, between x equals 2.5 and x equals 3. And so, let's see, part B, the fourth derivative of f satisfies the inequality f's fourth in absolute value is less than or equal to 48 when x is greater than 2. Let's see, Lagrange error bound for my approximation from part B. Okay, so I'm going to go over here, and I'm just going to say I'm looking for an error, which will be less than or equal to something. Let's see, I used a third degree, so n equaled 3. Okay, it was centered at x equals 3, and the approximation point was 2.5. Okay, so error is less than or equal to something divided by the next factorial, the maximum possible value of the fourth derivative, and that was 48. Okay, and then multiplied by the absolute value of 2.5 minus 3 to the fourth power, and that's going to be the Lagrange error bound. Okay, so that would be not. Oh, I guess if it called for a simplified fraction, I could say, okay, 48 over 4 times 6 is 24. Okay, that's going to be pretty easy to compute. Negative 1/2 to the fourth is 1 over 16. So that's going to be 2 over 16 equals 1 over 8. Okay, and then what is the coefficient of the x minus third term, or x minus 3 of the third power term of the Taylor series for f prime? Okay, well, let's just get, add in a kind of a ghost term over here. The next one would be 32 over 4 factorial times x minus 3 to the 4. If we took the derivative of that, we would have 4 times 32 divided by 4 factorial times this thing to the third. So that's going to be the coefficient. I guess we need to simplify that. So 4 times 4 times 2, I guess, divided by 4 times 3 times 2. So I'm going to start canceling stuff off, and I'm going to have 16 thirds. And that will be my simplified fraction. Okay, I think, yeah, that's going to be all for this extra set of practice problems. And I think this was a good, kind of variety of Lagrange error bound. We didn't have any graph situations, but I think we've seen some of those already in the homework and stuff. So that'll be all for this video. Thanks for watching.